All right, we're going to continue this unit on the nucleus today, and we're going to actually get into nuclear chemistry. So in nuclear chemistry, this is going to be the study of reactions that are caused by a change in the nucleus of an atom to actually become a new element. So this only involves our protons and neutrons in the nucleus, which you'll sometimes see them referred to as nucleons. So what makes something change into a new element versus not? What makes it stable versus unstable? So nuclear stability, there's two kind of general rules we take a look at. One is this large atom rule. The larger or more massive a nucleus is, the harder it is to stay together. So what scientists have found that elements with the atomic number greater than 83, so it has more than 83 protons, are always going to be radioactive, every single isotope of it. And that's due to an unstable proton to neutron ratio. So these elements have no known stable isotopes. Now, the small atom rule is that elements with an atomic number of 83 or less have at least one stable isotope, and then we'll have possibly one or more unstable isotopes. Now, one exception to this is technetium, and it has only unstable isotopes, and this is due to its proton to neutron ratio. So whether or not an isotope is going to be stable or unstable, so whether its nucleus is going to be stable or unstable, is going to be based on the ratio between the protons and the neutrons. So what happens when we have an unstable nucleus? Well, it's going to undergo transmutation. So nuclei naturally or spontaneously give off radioactive decay particles, and it causes it to change from one element into another in order to become more stable. So this process is transmutation, and you can think of that word mutation. So trans meaning I'm like changing from one to another. Mutation, you're undergoing a big change into something new. So transmutation, which is a definition that you need to know, is going to be this changing of a nucleus from one element into the nucleus of another new element. And it's going to do so by emitting decay particles, which just means giving them off. So what are these decay particles that can be given off? So we have three types of particles and one type of energy that we focus on. So the types of naturally released radiation would be alpha, beta, positron, and then gamma rays. So these first three are your actual particles, and then gamma rays we'll see in a minute are going to be pure energy. Alpha particles have the weakest strength. You can stop it with like a piece of paper. Beta particles and positrons, those are kind of in the middle. They're stronger than alpha particles, but not as strong as gamma rays. And then gamma rays is going to have the strongest strength. So sometimes you'll see this as the strength of its penetrating power in order to move through different materials. So one little thing when we talk about our different decay particles will be on table O. So that would be this table right here. This gives you a bunch of different symbols used in nuclear chemistry. We're going to talk about alpha, beta, positrons, and gamma radiation. So all these notations that I have are right on table O. And the reason why those are helpful with our radioactive particles, it gives us information about these different decay types. So for an alpha particle, which has the symbol here, you'll see the helium symbol because it's actually just the nucleus of a helium atom. The top number is going to be the mass of that decay particle. The bottom number is going to be the charge of the decay particle. So for an alpha particle, it has a mass of 4 and has a charge of +2. Okay, and when we see this undergo like this uranium-238 isotope, it gives off this alpha particle and changes into something new. So this is an example of like transmutation that we were just defining. A beta particle has a 0, -1 e. So this is essentially an electron being emitted from the nucleus, which we'll talk about in class and you'll see some more videos on. So with this one, it has a mass essentially of 0. You know, electrons have a really, really tiny, tiny fraction of a mass, and then has a charge of -1. A positron is actually very similar to a beta particle. They have essentially this mass of 0, but it has the opposite charge, +1. So those are the three types of decay particles that could get emitted from an unstable nucleus. The other type of radiation can be gamma decay or gamma radiation. This does not change the identity of the element, though, so it can be given off in terms of energy, but it doesn't actually change what the element is, so it doesn't force it alone to undergo transmutation. It has no mass or charge at all, and it's pure energy. So you'll see the notation on table O is this, 0/0, so no mass and no charge. It's the most dangerous, highly penetrating radiation, so it can cause the most damage to cells. So some ways that we detect what types of radiation can be observed when they pass through electric or magnetic fields. So with this big piece here of trying to answer questions on this is just remember that opposite charges attract. So if I see a type of radiation that bends towards the positive plate, it must have the opposite charge, negative, which would tell us it's probably beta decay. If it goes straight through and it's neutral, most likely it's going to be gamma decay. But say it goes and it bends towards the negative plate, it would have to have this positive charge. So it might be alpha decay, a positron. So just remember, if you kind of follow this idea of opposite charges attract, you should be able to figure out using, along with table O, which type of decay it might be. So I want you to take a second. We're going to go through a couple of questions before we talk about uses of these unstable isotopes. So for this first one, we have positrons and beta particles. So if you're using table O here, you have 0, -1e, and 0 + 1e. We can see that they have different charges, but they have the same mass. So this would be choice 2. Question number 2 here, in which type of reaction can an atom of one element be converted to an atom of another element? Okay, this is our definition, which would be number 3, transmutation. Okay, over on this side here, which nuclear emission has the greatest mass and the least penetrating power? So if you think about table O and in the notes, our greatest power was the alpha particle, and we also talked about how it has the weakest power, so it has the least penetrating power. So that's going to be choice 1. And then the last one here, which nuclear emission has no charge and no mass? So that would be the 0/0, okay, which would be our gamma, okay, which is that pure energy type of decay. All right, very last little part of the notes here is just some uses and risks of these unstable isotopes. So one little thing is that even though we think of radioactive isotopes as being dangerous, which they can be, there's a ton of beneficial uses. So one has to do with the irradiation of food. It can kill bacteria, it can allow it to be stored for a longer period of time. So it helps us in terms of being able to ship food or have it not being used for a period of time after it's been produced. Probably what you're familiar with from earth science is radioactive dating. So carbon-14 can be used to determine the age of once living remains. So, fossils is what usually comes to mind. So they'll measure the amount of carbon-14 compared to what it's changed into and be able to figure out how old the fossil might be. Uranium-238, which has a much, much longer half-life than carbon-14, can be used to determine the age of geological formations. So basically like rock formations or layers. And we can tell how old that is. There are also a variety of medical applications. These 3 you need to know. They tend to have shorter half-lives so that they can get quickly eliminated from the body so that they don't cause any damage to healthy cells in your body. So 3 that you need to be aware of would be iodine-131. So they're used to detect and cure thyroid disorders. Always look for iodine-131 tying in with thyroid. Technetium-99 is helped to detect tumors, especially brain tumors. And then cobalt-60 is actually a source of radiation in terms of like radioactive therapy of cancer, where it can help to get rid of cells in like tumors, cancerous cells. There are some risks, though, as you may be aware of radioactive isotopes, because any living tissue in the human body can be damaged by this radiation or the radioactive particles that we talked about. Now, your body is going to attempt to repair the damage, but sometimes the nature of it can't be repaired or is just too severe. So some risks that can come from radiation exposure might be damaging normal tissue. You can get mutations in DNA. It can cause illness, such as radiation sickness, and it can even cause death. Okay, so that's a little bit background information on radioactive isotopes. Why are they unstable, and what are some beneficial uses and risks involved?